A single pixel in a vast, empty darkness. That is our world in the legendary pale blue dot photograph. This image, captured by a robot millions of miles away, did more than humble us. It marked the beginning of a revolution in our cosmic story. Unmanned emissaries like Voyager and New Horizons have been quietly rewriting the history of our solar system, challenging everything we thought we knew about its birth and evolution. By the end of this journey, you will see our place in the universe through an entirely new lens, a perspective forged in the hard data sent back from the void. What if the outer solar system is not a frozen wasteland but a realm of hidden oceans and erupting ice? How did a simple fly shatter our models of planetary formation? The silent whispers from these deep space probes hold astonishing answers. What does it mean for our story when the universe itself keeps changing the script? That ambition was forged in an era of pure, unadulterated wonder. Long before microchips, the theoretical groundwork for space travel was laid by a reclusive Russian schoolteacher named Konstantin Tsiolkovsky. From his small, isolated home, he envisioned humanity breaking free from Earth, calculating the mathematics of rocketry with nothing but chalk and a powerful imagination. He famously declared that the Earth is the cradle of humanity, but one cannot live in the cradle forever. This poetic truth became the underlying philosophy for the probes that would eventually carry his ideas into reality. The political race to the moon provided the initial thrust, but the true, enduring legacy of that era would be these robotic Voyagers, built not for a quick flag planting, but for a journey spanning generations. The catalyst was a celestial event of breathtaking rarity. The outer planets, those distant giants, were slowly aligning in a way that happens only once every 176 years. This configuration meant a single spacecraft could use the gravity of one planet to slingshot itself toward the next, a cosmic pinball game on an unimaginable scale. They called it the Grand Tour. The opportunity was too perfect to ignore, a fleeting window in the cosmic clock, but seizing it required overcoming staggering obstacles. Securing funding for a mission that would not yield results for decades was a monumental political battle. Engineers had to invent technology from scratch, building a spacecraft with a brain less powerful than your modern car key fob, yet robust enough to survive intense radiation, micrometeoroid impacts, and the profound cold of deep space for over 40 years. Every component was a calculated risk, every system a masterpiece of redundancy. The goal was audacious. This was not merely about taking pictures of Jupiter or Saturn. It was about launching a message in a bottle into the cosmic ocean, an act of faith that would extend humanity's senses to the very edge of the solar system and beyond. The Voyager probes were our stand-ins, our eyes and ears on a journey we could only dream of taking ourselves. They were built with a simple yet profound primary mission. But as we would soon discover, their greatest achievements were the ones nobody had even thought to plan for. The first crack in our old cosmic story appeared not as a whisper, but as a violent eruption. As Voyager 1 closed in on Jupiter, its primary target was the giant planet itself, but its cameras also captured the 4 strange worlds orbiting it, one of which was the moon Io. Every scientific model predicted a cold, geologically dead place, a frozen rock pockmarked with ancient craters just like our own moon. The reality waiting in the deep space photographs was nothing short of a waking nightmare. Instead of a silent, icy sphere, Voyager saw a world painted in garish yellows, oranges, and reds, a color palette more reminiscent of a poisonous pizza than a planetary body. The surface was unnervingly smooth, completely devoid of the expected impact craters. It was as if the entire moon had been resurfaced, and recently. The mystery deepened when a young engineer named Linda Morabito was analyzing a navigation image. She noticed a strange, crescent-shaped plume extending from Io's limb, a faint curl against the blackness of space. At first, she thought it was an unknown moon, but there was no moon at that location. The only possible explanation was that she was looking at a volcanic eruption, a plume of material shooting hundreds of miles up from the surface of a world everyone thought was frozen solid. The discovery was a profound shock that reverberated through the entire scientific community. Io was not dead. It was the most volcanically active body in the entire solar system, a celestial inferno with fountains of fire rewriting the rules of geology before our very eyes. The immediate question was, what could possibly power such ferocious activity on a small moon so far from the sun's warmth? The old model of internal radioactive decay, the same slow heat that warms Earth's core, was completely insufficient. The answer was found in the brutal gravitational pull of its parent planet, Jupiter. Io is caught in an orbital tug of war between the massive gravity of Jupiter and the slight but persistent pulls from its neighboring moons, Europa and Ganymede. This constant rhythmic squeezing and stretching, a process called tidal heating, churns Io's interior with unimaginable friction, melting its very core. This finding shattered a fundamental assumption. We learned that geological life, the churning engine that shapes a world, does not require a star. A planet's gravity alone can forge a hellscape of fire and brimstone, turning a moon into a crucible of cosmic forces. This was the first major rewrite. It proved that our solar system was not a quiet, orderly place with a simple past. It was a dynamic, violent, and utterly surprising system, where entire worlds could defy our deepest expectations. And this was only the first surprise Voyager had in store. If Io was a world of fire, its neighbor Europa presented a mystery of ice. Voyager's images revealed a stunningly smooth, bright sphere crisscrossed with a seemingly random web of dark, rusty lines. It looked less like a moon and more like a cracked eggshell, a globe of ice polished to a brilliant sheen. The most shocking detail was what scientists did not see: impact craters. Every solid body in the solar system bears the scars of ancient bombardments, a cosmic history written in pockmarks. Europa's surface, however, was eerily young and unblemished. This could mean only one thing: the icy crust was being actively resurfaced, erasing evidence of impacts almost as soon as they occurred. The surface of Europa was a palimpsest, a page that was constantly being wiped clean. But what force could possibly achieve this? The answer, theorized by scientists like planetary geologist Robert Pappalardo, was as profound as it was simple: a vast, global ocean of liquid water hidden beneath the ice. The cracks we see are not canyons in solid ground, but fractures in a floating ice cap, stains from where slush and material from the ocean below had welled up to the surface. This single idea sent shockwaves through the field of astrobiology. We had always defined the habitable zone as that narrow, Goldilocks region around a star where water could remain liquid. But here was a world far beyond that zone, bathed in the perpetual cold of deep space, harboring an ocean containing more than twice the liquid water found on all of Earth. The heat source was not a nearby sun, but the same brutal gravitational kneading that tormented Io. Jupiter's relentless pull, flexing Europa's core, provided the internal warmth to keep a planet-wide sea from freezing solid. This was the second great rewrite of our cosmic story. life, we had to concede, might not be a perk of sunny, Earth-like worlds. It could be a tenant in sunless abysses, thriving in perpetual darkness under the ice of a distant moon. The universe had just expanded the real estate for potential life by an almost unimaginable degree, forcing us to reconsider not just where we should look, but what life itself could be. Europa's hidden ocean suggested life might thrive in sunless waters, but the next great revelation would come from a world where the very chemistry of life was turned on its head. The Cassini-Huygens mission, a successor to Voyager's legacy, arrived at Saturn and turned its gaze to the planet's largest moon, Titan. For centuries, Titan had been little more than a smudge of orange in our telescopes, a world shrouded in an impenetrable haze. But when Cassini's radar pierced that thick, soupy atmosphere, it unveiled a landscape that was both hauntingly familiar and utterly alien. The data revealed river channels carving through terrain, vast fields of dunes shaped by wind, and something that made scientists gasp: the glint of sunlight reflecting off the surfaces of standing lakes. This was a world with a complex geography we had only ever associated with Earth. The shock was not the presence of lakes, but what filled them. On the frigid surface of Titan, where temperatures plunged to negative 290 degrees Fahrenheit, water is harder than rock. The liquid that flows, evaporates, and forms clouds is not water, but liquid methane and ethane. The Huygens probe, which detached from Cassini and parachuted through the opaque atmosphere, gave us our first ground-level view. Its cameras showed a scene of rounded cobblestones on a damp riverbed, a landscape carved by fluids we could never swim in. This discovery forced a complete rewrite of planetary science. Titan possessed a full hydrological cycle, just like Earth's, but with methane as the working fluid. It has methane clouds, methane rain, and methane rivers that feed into methane seas. This proved that the complex geological and meteorological processes that shape a world are not unique to our own planet's particular chemistry. The forces of erosion, weather, and climate are universal, capable of operating with a completely different set of ingredients. Titan became more than just a moon. It transformed into a laboratory for understanding probiotic chemistry, the steps that lead to the emergence of life. Its thick atmosphere, rich in nitrogen and organic compounds, is constantly churning, creating the kind of complex molecules that are the building blocks of biology. This suggests that the fundamental pathways to life might not be a fluke of Earth's early environment, but a possibility that can arise in many different cosmic kitchens. The universe, it seems, has more than one recipe for a dynamic, evolving world. Yet even the bizarre chemistry of Titan was not the final surprise. A far smaller and seemingly insignificant moon of Saturn was preparing to deliver the most stunning revelation of all. Enceladus, a tiny, gleaming world of ice no wider than the state of Arizona, appeared to be just another frozen marble. But as the Cassini spacecraft made repeated close passes, its instruments detected something impossible. Gigantic geysers of water vapor and ice crystals were erupting from massive fractures near its south pole, shooting hundreds of miles into the blackness of space. This was not an ancient, dormant world. It was an active moon, violently venting the contents of a hidden ocean directly into the void. The discovery was so unexpected it felt like catching a secret in the act. Cassini did not just photograph these plumes, it flew right through them. Its cosmic dust analyzer sampled the material, tasting the composition of this alien ocean. The results sent a jolt through the scientific community. The plumes were not just pure water. They were rich in sodium chloride, ordinary table salt, along with tiny particles of silica. Most importantly, they contained a sprinkling of complex organic molecules, the carbon-based building blocks essential for life as we know it. In one breathtaking flyby, Cassini had confirmed three things. A global subsurface ocean existed. It was in contact with a rocky, mineral-rich seafloor, and it contained the fundamental chemistry for biology. This transformed Enceladus from a curiosity into the most promising habitable environment we have ever found beyond Earth. The implications rewrote the cosmic timeline for a fourth time. We had been looking for life in all the wrong places, focusing on planets basking in the warmth of their stars. But here was a small, icy moon, warmed only by the gravitational flexing of its planet, offering a complete recipe for life, water, energy, and organic compounds. The search for life was no longer about finding another Earth. It was about finding the next Enceladus, an ocean world hidden beneath a shell of ice, silently venting its secrets to the universe. The final and perhaps most humbling rewrite came from the solar system's edge, from a world we had written off as a frozen fossil. When the New Horizons probe raced past Pluto in 2015, it delivered a data stream that systematically dismantled every expectation. This was not the dead, cratered iceball of textbook diagrams. It was a stunningly complex and vibrant world. The probe's cameras captured towering mountains of water ice, as hard as granite at those temperatures, jutting into a thin, hazy sky. It mapped vast, flowing plains of solid nitrogen, glaciers that slowly oozed across the landscape like cosmic taffy. Most astonishing of all was its atmosphere, a delicate, layered haze that extended far into space, a beautiful and dynamic shroud around a world that was supposed to be inert. How could a body so small and so far from the sun, receiving only faint whispers of solar warmth, possibly be so active? The presence of these features pointed to one inescapable conclusion: recent geological activity. For principal investigator Alan Stern and his team, the evidence was undeniable. Those young, uncratered plains suggested the surface had been resurfaced within the last 100 million years, a blink of an eye in cosmic terms. The towering mountains required a powerful internal heat source to thrust them upward. The most compelling explanation for all of this activity was the possibility of a subsurface ocean, a layer of liquid water sloshing beneath the ice, kept warm by the decay of radioactive elements in Pluto's core and the residual heat from its violent birth. This single idea forced the fifth and final major revision of our cosmic story. It completely reshaped our understanding of the Kuiper Belt, that vast graveyard of icy leftovers beyond Neptune. We had assumed these objects were pristine time capsules, static and unchanging relics from the solar system's dawn. Pluto proved they are not inert fossils. They can be dynamic, evolving worlds in their own right. This discovery pushed the boundary for geological life into the deepest, coldest reaches of our system. If a small, isolated world like Pluto can harbor the heat and complexity for ongoing change, then the potential for active worlds and perhaps even hidden oceans is nearly limitless. Our cosmic timeline is no longer a simple story of a fiery birth followed by a long, quiet freeze. It is a narrative of persistent, surprising activity, driven by forces we are only beginning to comprehend, happening everywhere we dare to look. But the most profound rewrites were not confined to the planets and moons themselves. They extended to the very boundary of our solar system, to the edge of the sun's influence. For generations, astronomers had pictured the Heliosphere as a sleek, comet-like shape, a smooth bubble carved out by the solar wind as our star moved through the galaxy. This was the clean, simple diagram found in every textbook. The reality, as the Voyager probes discovered, was a chaotic and magnificent mess. After their decades-long journeys, as each spacecraft punched through the invisible boundary known as the heliopause, their instruments sent back a torrent of unexpected data. Instead of a defined, stable wall, they found a turbulent and porous frontier, a frothy magnetic barrier more like a writhing cloud of plasma. This was not a clean exit from the solar system, but a complex, interactive zone where the sun's particles battled with the powerful winds of interstellar space. The discovery, led by Voyager project scientist Ed Stone, forced a complete overhaul of our models. The protective bubble that shields our entire planetary system from the harsh radiation of the galaxy is not a static shield. It is a dynamic, ever-shifting entity full of magnetic bubbles and cosmic turbulence. This means our solar system does not simply drift through an empty void. It is actively interacting with the galactic medium around it, its outer skin constantly reshaping itself in a complex cosmic dance. Our local neighborhood, it turns out, is far stranger and more intimately connected to the galaxy than we ever dreamed. Deep within the void, as Voyager 1 journeyed toward the edge, its instruments detected something profoundly strange. The solar wind, that constant million-mile-per-hour stream of charged particles flowing from the sun, suddenly dropped to a whisper. It was as if the spacecraft had sailed into a vast celestial doldrums, a place scientists called the stagnation region. Here, the wind slowed to a crawl, and the sun's magnetic field piled up, growing denser and more intense. This was not part of the plan. The models predicted a gradual, orderly decline, not a traffic jam of cosmic forces at the final frontier, but the true shock lay just beyond. As Voyager pushed further, it entered a zone of pure magnetic chaos. The sun's orderly magnetic field lines, which usually sweep out in elegant arcs, were shattering and reconnecting in a frenzied dance. This created a frothing sea of magnetic bubbles, each one tens of millions of miles wide, a foam of cosmic energy. The textbook image of a sleek, comet-shaped heliosphere was instantly obsolete. We had not sent a probe to cross a simple boundary. We had sent it into a turbulent, bubbling whirlpool where our solar system meets the galaxy. The analysis from the Voyager team, led by the persistent Ed Stone, forced a complete rewrite of heliospheric physics. Our home in space is not encapsulated by a smooth, solid shield. It is protected by a porous, frothy interface, a dynamic filter where the sun's influence and the galactic wind engage in a constant, unseen battle. This discovery resonates far beyond our own cosmic neighborhood. If our sun's protective bubble is this complex and messy, then every other star system in the Milky Way likely possesses a similar, intricate magnetic personality. The universe is not filled with isolated islands, but with interacting spheres of influence, each one a roiling frontier of magnetic foam. Beyond that frothing magnetic frontier, Voyager 1 began a completely new kind of science. It was now a true interstellar probe, and its instruments were turned toward the cosmic ocean itself, measuring the high-energy particles that stream from distant supernovas and black holes. These are galactic cosmic rays, the raw material of the galaxy, and for the first time we could sample them directly, without the sun's protective bubble filtering the signal. The data sent back was startling. The density of these powerful particles was far more intense than anyone had predicted. Out there, in the void between stars, space is not empty. It is flooded with a relentless, invisible rain of atomic shrapnel moving at nearly the speed of light. This revelation forced an immediate and crucial recalibration of our understanding of deep space radiation. For future astronauts on long journeys to Mars or beyond, this intense particle bath represents a significant health hazard, a constant background threat that shielding and mission plans must now account for with far greater seriousness. But this discovery also provided a priceless gift, a clean baseline. By measuring the cosmic rays from outside, Voyager gave us a reference point to understand how the Sun's own activity, its 11-year cycle of storms and quiet, modulates the radiation that actually reaches us in the inner solar system. We can now see with perfect clarity how our local star's weather interacts with the powerful gusts of the galactic wind. Our home star and the wider galaxy are locked in a continuous, invisible dance, and for the first time we have a front-row seat to the performance. The journey of discovery did not end at Pluto. The New Horizons probe, its primary mission a spectacular success, raced onward into the deep freeze of the Kuiper Belt. This vast region of icy remnants was a cosmic frontier we had only seen as faint points of light, a graveyard of frozen fossils from the solar system's birth. The probe's new target was a small, enigmatic world named Arrokoth, a name meaning sky in the Powhatan language. As the spacecraft closed in, its cameras revealed a sight that defied all imagination. Arrokoth was not a simple sphere or a lumpy rock. It was a celestial snowman, a perfect contact binary composed of two distinct, flattened lobes gently pressed together. Its shape, resembling two thin pancakes fused at their edges, was unlike anything we had ever seen up close. The surface was a pristine, reddish landscape, untouched by the heat of the sun or the violence of planetary migration for over 4 billion years. This was not a world sculpted by later forces. It was a perfect, frozen snapshot of our solar system's raw construction material. The very form of Arrokoth presented an immediate and profound puzzle. How did these two separate objects come together so perfectly? The old model of planetary formation, known as hierarchical accretion, pictured a violent, chaotic process. In that story, countless small planetesimals would have careened through space, smashing into each other at high speeds to gradually build larger bodies. A collision like that would have shattered Arrokoth, leaving a scarred and mangled wreck. But this object was serene, its two lobes resting together in a union so gentle it seemed almost peaceful. The evidence pointed toward a completely different origin story, a process called Pebble accretion. Imagine a quiet, dusty disk of gas and pebbles swirling around the infant sun. Within this disk, small particles would have gently clumped together, not through violent impacts but through static electricity or simple collisions at walking speed. These small clusters would have grown, their gravity so faint that when two of them met, they would have simply drifted together, merging in a slow, cosmic dance. Arrokoth was not built by a crash, it was formed by an embrace. This single, distant object rewrote the earliest chapter of our cosmic timeline. The building blocks of our entire planetary system, from Earth to Jupiter, may not have been forged in a chaotic firestorm of destruction. Instead, they could have assembled quickly and gently from a sea of pebbles, a peaceful beginning to the story that eventually led to us. The violence would come later with the dramatic migration of the giant planets. But the very first steps, the creation of the seeds from which worlds would grow, might have been a quiet and orderly affair. Arrokoth is more than a fossil. It is a testament to a gentler genesis, a fundamental rewrite of our own origin story written in ice at the edge of the light. This solar wind, the very same river of particles Voyager measured slowing to a crawl at the edge of darkness, begins its journey in a place of unimaginable violence. While our probes were mapping the outer frontiers, another daring mission was flying straight into the furnace itself. The Parker Solar Probe is a technological marvel, a shield carbon composite shield designed to withstand temperatures hotter than a blast furnace, all while performing a feat that borders on science fiction, repeatedly diving through the sun's outer atmosphere, its corona. For the first time, we are not just observing our star from a safe distance. We are touching it. The data streaming back is more than just new information. It is a revolution in solar physics, forcing us to rewrite the story of the star that gives us life. The probe's first major discovery was as bizarre as it was unexpected. It found the solar wind near the Sun is not a smooth, steady flow. Instead, it is riddled with what scientists call switchbacks, sudden and gigantic S-shaped kinks in the Sun's magnetic field. Imagine a perfectly straight highway near the surface of the Sun, and without warning, the road violently flips into a massive S-curve, hurling particles sideways at incredible speeds before snapping back straight again. These switchbacks are not minor ripples. They are colossal structures, sometimes larger than planets, and they appear to be pumping enormous energy into the solar wind, acting like cosmic whips that accelerate particles to the million-mile-per-hour speeds we detect far out in the solar system. This single finding has turned the search for the solar wind's engine into a whole new investigation. We now know the wind is born in a storm of magnetic chaos, a reality our old, calm models never accounted for. Parker also solved a centuries-old mystery about the dust that fills our inner solar system. As it flew closer to the Sun, it confirmed the existence of a theorized dust-free zone. Within a certain distance, the Sun's immense heat vaporizes all interplanetary dust, turning it into a thin, incandescent gas. This creates a strangely pristine cavity around our star, a region scrubbed clean by its ferocious power. But Parker's ultimate gift is its ability to rewind the cosmic clock. By understanding the precise mechanisms that heat the corona to millions of degrees and fling the solar wind into space, we are not just learning about the Sun today. We are building a perfect model of its behavior, a template we can run backward in time. We can now simulate with far greater accuracy how the Sun has evolved over its 4.6 billion-year life, how its violent youth, filled with more frequent and powerful storms, might have stripped away the early atmospheres of worlds like Mars, and how its steady, reliable middle age has granted our own planet a long, stable window for life to flourish and thrive. The Sun's past is the key to understanding the history of every planet that orbits it, and for the first time we are holding that key in our hands. Even the most distant journeys of our robotic Voyagers provide clues about realms they will never see. Far beyond the Kuiper belt, in the profound darkness where the Sun is just a particularly bright star, lies the final frontier of our solar system, the theorized Oort cloud. This is not a flat belt, but a vast spherical shell of trillions of icy bodies, a cosmic deep freeze believed to extend nearly halfway to the next star. No spacecraft will ever reach it within our lifetimes, yet the paths of Voyager and New Horizons are helping to prove it is really there. The evidence comes not from a camera image, but from the subtle, silent language of gravity. As these probes speed toward interstellar space, their trajectories are being minutely tracked. Tiny, unexplained deviations in their speed and course, slight gravitational tugs, act as fingerprints of unseen mass. By analyzing these minuscule perturbations, scientists can infer the gravitational pull of the vast, diffuse shell of material that makes up the Oort cloud. It is a form of celestial cartography using a spacecraft's path to map the invisible. This gravitational data is complemented by another cosmic clue, the long-period comets. These brilliant visitors, which take thousands or even millions of years to complete a single orbit, seem to arrive from all directions, not just from the flat plane of the solar system. This random distribution points directly to a spherical reservoir of icy objects, a shell surrounding us. By tracing the paths of these comets backward, astronomers can estimate the Oort cloud's immense size and total mass. The picture emerging from this indirect evidence is startling. The Oort cloud is not a sparse and static collection of relics. The data suggests it may be far more massive and dynamically active than we ever pictured. Its vast population of icy worlds are not perfectly stable, their orbits gently stirred by the combined gravity of passing stars and the Milky Way itself. This constant, subtle gravitational nudging is what occasionally sends a frozen citizen of this distant realm falling inward toward the sun, transforming it into the spectacular comet that graces our skies. In this way, our farthest-flung probes are the ultimate pathfinders. Their long, silent journeys are helping us confirm the final chapter of our solar system's formation story, proving that the cloud of icy debris from which we formed did not simply vanish. It remains with us still, a colossal, invisible boundary defining our true home in the galaxy. These silent, frozen surfaces are becoming the ultimate timekeepers for our solar system. The accepted age of 4.6 billion years is not being thrown out, but it is being meticulously refined by the data from our farthest-flung probes. We can think of crater counts as a kind of cosmic clock. The more craters that scar a world's surface, the older that terrain is presumed to be, having spent more time exposed to the relentless rain of asteroids and comets. For decades, our primary reference point was our own moon, its heavily pockmarked highlands serving as the gold standard for dating the entire inner solar system. But what if that standard was incomplete? The flyby of Pluto and its large moon Charon gave us a revolutionary new data point. Here were two worlds locked in the deep freeze of the Kuiper belt, their surfaces preserved in a state of near-perfect geological stasis for billions of years. When scientists counted the craters on these pristine landscapes, they expected to see a record of extreme, relentless bombardment. The reality was more complicated and far more interesting. The cratering record on Pluto and Charon did not perfectly match the story told by the Moon. The evidence suggests that the cataclysmic period known as the Late Heavy Bombardment, a time when the inner planets were supposedly pummeled by a sudden spike in impacts, may not have been a single dramatic event. Instead, the new data paints a picture of a more prolonged and complex period of violence, one that might have started earlier or lasted longer than our lunar-centric models suggested. This recalibration is like finding a second, independent clock that forces us to check the first one. The implications ripple across the entire solar system. If the bombardment's timeline was different, then the window when Earth and Mars were being brutally sterilized by impacts might have closed at a different time. This directly affects our understanding of when stable, habitable conditions could have emerged, and when the fragile chemistry of life might have first taken hold on our own planet. Our robotic probes are not just explorers of space, they have become forensic historians, using comparative planetology to calibrate the solar system's geological clock with a precision we never thought possible. This same precision navigation is now hunting for ghosts. The trajectories of our farthest-flung probes are so exquisitely tracked that their paths act as the most sensitive scales imaginable, weighing the entire solar system's gravity. Every subtle nudge, every minuscule change in velocity, is a potential clue. A tiny, unexplained deviation in a probe's expected course could be the signature of an unseen mass, a hidden world whose gravity is gently tugging on our robotic emissaries from the dark. The hypothetical planet 9 is the most famous of these phantoms, a potential giant lurking in the frozen expanse far beyond Pluto. While no probe has yet sent back the definitive data that screams its discovery, their journeys are performing a different, equally vital task. By confirming that their paths match predicted models with astonishing accuracy across vast distances, they are systematically ruling out entire swaths of space. They are telling us where this hidden world is not. Each successful, uneventful flyby and each precisely tracked cruise phase places a new constraint, shrinking the possible hiding places on the cosmic map. This transforms our spacecraft into something new, not just explorers, but ultra-sensitive gravity detectors. They are feeling their way through the darkness, their silent journeys tracing the invisible contours of mass in our solar system's most distant and unknown territories. The very absence of a major gravitational anomaly is a profound piece of data, forcing us to refine our theories and focus our search. It is a meticulous process of elimination, a celestial forensics where the suspect has yet to be seen, but the evidence of its potential influence is being carefully, painstakingly gathered. Out in the true void, the Voyager probes are no longer just explorers. They have become our first permanent space weather stations in the galaxy, their instruments constantly monitoring the conditions of our local galactic neighborhood. They are measuring the strength and direction of the magnetic fields that flow between the stars and taking the temperature of the sparse, superheated plasma that fills the void. This is not abstract data. It is a live report from the specific region of space our solar system is currently traversing, a place known as the local interstellar cloud. Think of it as the solar system sailing through a vast but distinct oceanic current within the wider galactic sea. This cloud is a region of slightly warmer, less dense gas than the surrounding interstellar medium, and by characterizing its properties, we are learning how the galaxy itself directly molds the protective bubble of our heliosphere. The pressure and magnetic fields of this cloud press in on the sun's influence, shaping the very shield that protects every planet from the harsh radiation of deep space. This means the climate of our entire solar system, the intensity of cosmic rays that reach Earth, and the stability of our planetary environment are not solely dictated by the sun. They are part of a much larger conversation with the galaxy. For the first time, we are gathering the data to understand that conversation, watching as our entire cosmic neighborhood rides through a changing galactic weather pattern that unfolds over thousands of years. Yet these robotic explorers carry a purpose that extends far beyond their scientific instruments. The Voyager and Pioneer probes are on permanent escape trajectories, having broken free from the sun's gravitational hold. They are now untethered wanderers, set to drift through the vast expanses between stars for billions of years. Their ultimate fate is to become relics in the galactic archive, silent travelers on a journey that will outlast our world. They carry with them artifacts of a species that once looked to the stars and sought to make its mark, the golden records and the pioneer plaques. These are not merely scientific packages, but time capsules crafted for an audience we can scarcely conceive of. Etched with symbolic instructions and carrying the sounds and images of Earth, they are messages in a bottle cast into the cosmic ocean, intended for any potential finder in the distant future. This single act of dispatching a greeting card into the void forces a profound shift in perspective. It compels us to consider our legacy on a truly galactic timescale. These probes will continue their silent voyage long after human civilization has faded, long after the Earth has been consumed by the dying sun, and even after the Milky Way has merged with other galaxies, its current spiral form lost to time. They are the most durable artifacts our civilization will ever produce, bearing witness to a fleeting moment of technological awakening. In their endless journey, they connect our brief, brilliant history to the unimaginably vast future of the universe itself, a quiet testament that we were here and we reached out. These silent wanderers have given us more than just cosmic discoveries. They have fundamentally reshaped our own world. The monumental challenge of building a machine to survive for half a century in the void forced us to invent technologies that seemed like science fiction. Every single component had to be more reliable, more efficient, and more robust than anything ever built before. This relentless demand for perfection created a wave of innovation that quietly rippled back to Earth, transforming our daily lives in ways we rarely stop to consider. The most profound legacy of these missions may not be written in the stars, but in the devices we hold in our hands. The need to capture detailed images of distant worlds with a camera that used almost no power led directly to the development of the CMOS image sensor. This tiny, revolutionary chip is the reason every modern smartphone has a powerful camera. The act of photographing Jupiter's storms ultimately gave us the ability to share pictures of our lives instantly with the entire world. The very computers that guide these probes had to be marvels of resilience. They were built with fault-tolerant systems, designed to identify and work around their own failures, because a crashed computer millions of miles away could not be rebooted. This philosophy of building systems that can self-diagnose and self-repair became the bedrock for critical technologies on Earth, from the flight computers in commercial airliners to the networks that power our global financial systems. Even the quest for power in the sunless outer solar system yielded a radical solution. The radioisotope thermoelectric generators, or RTGS, are essentially nuclear batteries. They harness the steady heat from the decay of plutonium and convert it directly into electricity with no moving parts. While you will not find an RTG in your car, the intense research into these systems advanced our entire understanding of using nuclear power for long-duration, remote applications. The materials science developed to shield these power sources and protect the spacecraft from extreme temperature swings has since been adapted for use in medical devices, improving the safety and longevity of life-saving implants like pacemakers. This is the beautiful, unspoken feedback loop of exploration. The cosmic ambition to reach into the unknown did not just expand our understanding of the universe, it accelerated our own technological evolution. We reached for the planets, and in doing so, we built a better world right here at home. That cosmic patience is tested by a profound earthly limitation: the agonizingly slow trickle of data from the edge of darkness. While a Mars rover can beam back high-definition panoramas in a matter of hours, a probe like Voyager or New Horizons transmits its treasures at a pace that would feel archaic even in the earliest days of the Internet. From billions of miles away, its signal is so faint that by the time it reaches Earth, the power arriving at our giant radio dishes is over 20 billion times weaker than what it takes to run a digital watch. We are listening for a whisper in a hurricane. This forces data rates to plummet to a glacial speed, sometimes as slow as a few hundred bits per second. At that rate, downloading a single average smartphone picture could take days, and a full flyby's worth of information requires months or even years to completely transfer. This is not a design flaw, it is a simple, brutal law of physics. The vastness of space itself imposes a mandatory deliberation on our discovery. There is no instant gratification at the frontier. A probe screams past a new world in a matter of hours, its digital recorders filled to the brim with captured light and sensor readings, and then it begins the long, quiet task of whispering its secrets back to us, one precious bit at a time. This slow drip of cosmic truth has fundamentally shaped the scientific process. It creates a prolonged period of analysis, a slow unfolding of a mystery where the full picture only emerges piece by piece. Scientists receive the most spectacular images first, the ones that make headlines, but the real revelations are often buried in the subsequent data, in the spectral lines that reveal atmospheric composition or the particle counts that hint at a hidden ocean. This extended timeline allows for careful scrutiny and, crucially, for new perspectives to be applied. A graduate student looking at data that is 5 years old might see a pattern that the original mission scientists missed, leading to a breakthrough no one anticipated. The most profound rewrites of our cosmic story were not always announced in a flash of instant understanding. They were often uncovered slowly, patiently, as if the universe was demanding we take the time to truly listen. This slow data stream is a humbling reminder that the greatest discoveries are not just about collecting information, but about learning how to truly see what we have found. That faint whisper from the void is a constant test of our resolve. To even hear the Voyager probes, we built a planetary-scale ear, the Deep Space Network. This is a triad of colossal radio dish complexes, strategically placed in California, Spain, and Australia, so that as Earth rotates, at least one sight can always be pointed at any spacecraft in the sky. Each massive, steerable antenna is a masterpiece of engineering, a parabolic bowl of metal precisely shaped to catch unimaginably weak signals from the edge of nothing. The numbers are almost incomprehensible. The total power received from Voyager after its signal has traveled for over 22 hours across 14 billion miles of space is about 20 billion times weaker than the tiny trickle of energy that powers the memory in a digital watch. We are not just listening for a needle in a haystack, we are listening for a single, specific piece of dust on that needle in a hurricane. This monumental challenge forced a revolution in how we handle information. Engineers had to invent new forms of data compression and sophisticated error-correcting codes, complex mathematical algorithms that can rebuild a damaged signal from its scattered pieces. Think of it as trying to hear a friend whisper a sentence from a mile away in a thunderstorm. You might only catch one in every 10 words, but if the sentence is crafted with a special code, your brain can fill in the blanks and reconstruct the entire message perfectly. This technology, born from deep space desperation, is now the bedrock of everything from reliable Wi-Fi and crystal-clear cell phone calls to the flawless streaming of digital movies. Our cosmic ambition quietly fixed our earthly communications, yet we are fighting a fundamental law of physics, the inverse square law. It dictates that with every doubling of distance, a signal becomes not just twice as weak, but 4 times weaker. This is a battle we are destined to lose. The data stream from Voyager, once a torrent of images and readings, has slowed to a barely perceptible trickle of health data and particle counts. One day, perhaps within the next decade, its power will fade enough that its signal will drop below the threshold of our most sensitive ears. The Deep Space Network will listen, but it will hear only silence. Our tether will snap. These robotic pioneers will then complete their final transformation, from active explorers into permanent silent wanderers, carrying their golden records into the galactic night, their mission of discovery handed over to the cosmos itself. That fragile image of our world, a single pixel in the emptiness, did more than redefine our science. It rewired our very psyche. The iconic pale blue dot photograph, alongside the earlier Earthrise image from the Apollo missions, triggered a global shift in consciousness. For the first time, we saw our home not as an infinite landscape, but as a solitary, delicate oasis suspended in a vast and inhospitable blackness. This was not just a new perspective, it was a profound emotional awakening. Our tribal squabbles and national borders vanished, replaced by the stark reality of a shared, fragile biosphere adrift in the cosmic dark. This new self-awareness, this concept of Spaceship Earth, was a direct gift from our robotic ambassadors. They gave us the ultimate outsider's view, and in doing so, they forged a new planetary identity. Yet at the same time, these probes were revealing a universe teeming with unexpected activity. The discovery of erupting volcanoes on Io and hidden oceans on Europa shattered the old, quiet model of the solar system. We learned that our cosmic neighborhood is not a static museum, but a dynamic and often violent frontier, full of hidden forces and surprising possibilities. This dual realization reshaped our collective soul. we are simultaneously more isolated and more connected than we ever imagined. We are the caretakers of a precious, lonely world, yet we are also citizens of a spectacularly diverse and active cosmic archipelago. This knowledge has democratized the heavens. Every new image from a probe at Saturn or a rover on Mars is instantly beamed across the globe, making anyone with an internet connection a virtual explorer. We all watched in unison as a spacecraft plunged through the plumes of Enceladus, and we all shared the collective gasp at the sight of Pluto's heart. We are no longer merely Earth-bound creatures looking up at distant points of light. We are a species that has extended its senses across the solar system, transforming abstract stars into tangible worlds, each with its own unique story of fire and ice. These silent voyagers have gifted us a new narrative for ourselves, transforming humanity from a localized phenomenon into a spacefaring civilization in mind and spirit, long before our bodies can make the journey. This shift from cosmic eavesdropping to local investigation is perhaps the most profound legacy of our deep space probes. For decades, the search for intelligent life was a patient, almost philosophical endeavor, centered on pointing giant radio telescopes at distant stars and hoping to catch a fleeting, artificial signal. The data from Voyager and Cassini changed the entire conversation. When these missions confirmed that Europa and Enceladus possess the three fundamental ingredients for life: liquid water, chemical energy, and organic compounds, they did more than just add new targets to a list. They fundamentally redefined what it means to search. We are no longer just listening for a distant hello. We are now planning missions to look for a neighbor's footprints, or perhaps their microscopic equivalents, right in our own cosmic backyard. This is a pivot from passive hope to active exploration. The compelling evidence of subsurface oceans provided the scientific justification for ambitious projects like the Europa Clipper, a spacecraft designed not merely to fly by, but to conduct a detailed reconnaissance of that icy shell, mapping its thickness and searching for the chemical signatures of biological activity. The ultimate goal, a lander that could one day melt or drill through the ice to directly sample the hidden ocean, is no longer science fiction. It is a direct consequence of the data streams sent back by our robotic pioneers. This transforms the search for extraterrestrial intelligence into something far more tangible. We are not just waiting for a message. We are preparing to go knocking on the door of a dark, alien ocean, with our deep space probes having already provided the convincing doorbell. That price tag for the entire Voyager mission, $865 million, sounds immense until you place it in context. It is a fraction of what a single modern aircraft carrier costs, a fleeting moment in the vast annual budget of any major nation. So how do we measure the return on an investment that yields no traditional products, no mined resources, and no new territory to claim? The true accounting is not found on a balance sheet, but in the quiet revolutions that ripple back to Earth. The relentless challenge of sending a fragile machine into the void forced innovations in computing, material science, and communications that have since become woven into the fabric of our daily lives. The fault-tolerant systems designed to keep a spacecraft alive for 50 years are now the bedrock of global finance and air travel. The need to capture crisp images with minimal power gave us the camera in every smartphone. We reached for the planets, and in doing so, we built a better world right here at home. Beyond the technology, there is a currency of inspiration. The stunning images and profound discoveries from these probes have ignited the imaginations of countless children who grew up to become the scientists and engineers solving earthly challenges in medicine, energy, and climate science. This is a generational investment in human capital, fueling a pipeline of innovation for decades to come. The missions also forge unprecedented global collaboration, uniting the world's brightest minds in a shared, peaceful endeavor that transcends borders. When a new image from the edge of the solar system arrives, it belongs to all of humanity. Can we truly put a price on rewriting our own origin story? The value of understanding where we came from, of seeing our world as a fragile pale blue dot, and of knowing that our solar system is a dynamic, living neighborhood is arguably priceless. These probes are our ultimate act of faith, an investment not in concrete and steel, but in knowledge, perspective, and the boundless potential of the human spirit to reach beyond its cradle. The next chapter of this great rewrite is already being assembled in clean rooms here on Earth. A new fleet of robotic explorers, armed with the questions their predecessors uncovered, is preparing to journey back to those enigmatic ocean worlds. The European Space Agency's JUICE mission and NASA Europa Clipper are not mere repeats of the Voyager flybys. They are dedicated orbiters designed to spend years weaving through the gravitational fields of Jupiter's moons, conducting the most detailed reconnaissance of Ganymede and Europa ever attempted. Their advanced radar will pierce the icy crusts, measuring for the first time the depth and volume of those hidden seas. Their mass spectrometers will analyze the composition of faint plumes, hunting for complex organic molecules. This is a shift from taking snapshots of these worlds to moving in and studying them as the dynamic, living systems we now believe them to be. Meanwhile, on the drawing board of the future, a mission of breathtaking audacity takes shape. NASA Dragonfly is not a rover. It is a nuclear-powered drone, an 8-rotor aerial vehicle designed to fly through the thick, hazy atmosphere of Titan. It will land, sample the organic rich sands, and then lift off again to fly dozens of miles to a new site, transforming a single landing point into an entire regional survey. This mission will literally taste the chemistry of Titan's surface, seeking to understand the probiotic steps that could lead to life in an environment of liquid methane. These are not just incremental upgrades. They represent a fundamental evolution in our strategy. We are moving from proving these oceans exist to asking what lives within them. The instruments on these new Voyagers are fine-tuned to detect not just the conditions for habitability, but the chemical signatures that life itself leaves behind, the biosignatures that would signal we are not alone in this cosmic story. The silent whispers from the void prompted these questions. The next generation of probes is being sent to listen for the answer. Yet for all the revelations they have sent back, these robotic explorers also teach us a profound lesson in humility. They are scouts, not settlers, and their vision is constrained by the very technology that gave them life. Each probe is a time capsule of human ingenuity from the era it was built, carrying the limits of its age into the cosmos. Its instruments are designed to answer the questions we thought to ask decades ago, not the ones its own discoveries force us to consider today. A spacecraft flying past an alien world at 30,000 miles per hour cannot stop. It cannot change its trajectory to investigate a strange glint on the surface or to follow a curious plume for a closer look. It is a bullet of pre-programmed inquiry, and its window for observation is terrifyingly brief. A human geologist on the ground would see a strange rock formation and immediately walk over to tap it with a hammer to feel its texture and understand its context within the landscape. Our robotic proxies can only take a picture from a distance and move on, leaving a universe of questions unanswered in their wake. They provide us with breathtaking snapshots, but a snapshot cannot capture the full, flowing story of a world. The most critical limitation is one of return. These missions send back data, but they cannot send back the things themselves. They cannot scoop a piece of that alien ice from Enceladus and bring it home to our most advanced labs. They cannot package a vial of Titan's methane damp sand for analysis under 1,000 different microscopes. The true, complex history of these worlds, written into the very atoms of their rocks and the complex chemistry of their oceans, remains locked away. The probes have performed a miracle, giving us the first true map of our cosmic backyard and circling the most astonishing destinations in bright red ink. They have handed us a list of profound mysteries, but solving those mysteries requires a new kind of presence. The next great rewrite of our cosmic story will not be written by a fleeting flyby. It will be penned by landers that taste the soil, by rovers that traverse the cracks in an icy shell, and perhaps one day by human explorers who can look upon these alien landscapes with their own eyes and finally ask what lies beneath. This cosmic perspective, built from decades of data, forces a quiet but profound philosophical reckoning. We are not living in a finished, static museum where the planets are merely decorative exhibits from a long-completed past. Instead, we inhabit a dynamic and violently evolving system, a cosmic construction zone where worlds are actively being reshaped by forces we are only beginning to comprehend. The most humbling realization is that the conditions for life itself appear to be startlingly common, not in the sunny, Earth-like gardens we once envisioned, but in the lightless, crushing abysses beneath the ice of distant moons. This single discovery strikes at the very heart of an anthropocentric worldview, the deeply ingrained belief that humanity, and the life that formed on our particular world, sits at the center of cosmic importance. The universe is not fine-tuned for us. We are a consequence of its physical laws, not the reason for them. The cosmic timeline is not a human story. It is a grand, physical narrative of gravitational collapse, planetary migration, and chemical evolution, a story that has been unfolding for over 4.5 billion years. Our entire recorded history, every empire and every individual life, is a single, fleeting sentence written on the very last page of an epic volume. These robotic Voyagers hold up a mirror to all of humanity. In their stunning success, we see the reflection of our own ingenuity, our boundless curiosity, and our drive to reach beyond our cradle. But in the vast, silent vistas they transmit back, we are confronted with our profound smallness. We are a species on a tiny, fragile world, a pale blue dot adrift in an overwhelming and majestic darkness. The ultimate gift of these missions is not just a new map of the solar system, but a new understanding of our place within it, a perspective that is at once humbling and infinitely inspiring. These silent journeys through the void are not the work of a single nation. They are monuments to international collaboration, a testament to what humanity can achieve when we unite under a common banner of curiosity. While missions like Voyager and Cassini were led by agencies like NASA and the European Space Agency, they are powered by global scientific teams and a worldwide network of tracking stations. The stunning success of the Huygens probe, which touched down on the alien surface of Titan, is a perfect example. This lander was built by the European Space Agency, but it was carried across 1 billion miles of space by NASA Cassini orbiter, a 7-year voyage of perfect coordination between continents. Once the data arrives on Earth, it is not hoarded. It is shared openly with the global scientific community, a river of raw cosmic truth that any researcher, anywhere, can tap into to accelerate the pace of discovery for all of us. This model of peaceful, cooperative exploration stands in stark contrast to the terrestrial conflicts that so often define our history. It demonstrates with quiet and undeniable force that our greatest achievements occur not when we build walls, but when we work together toward a goal that transcends any single flag. The quest to understand our cosmic timeline has, in a small but profoundly significant way, helped to build a more unified human community, one focused on a shared future written in the stars. Their endurance is a quiet miracle of foresight. Built with the technology of the 1970s, the Voyager probes were engineered for a journey longer than the professional lives of their creators. Every system was a lesson in designing for deep time, an era where no repair mission could ever reach them. The engineers knew that failure was not an option, so they built in layers of redundancy. Critical systems like computers and transmitters were often triplicated. If one unit faltered, another would seamlessly take its place, a silent relay race across the void. This philosophy extended to their very brains. The Voyagers carry computers with a tiny fraction of the processing power found in a modern car key fob. But that simplicity is their strength. With fewer components and no moving parts, there is simply less that can break. These machines are not fast, they are steadfast. They were also hardened against an invisible enemy, cosmic radiation. The space between planets is flooded with high-energy particles that can scramble delicate electronics. The probe's vital components were shielded and built using radiation-hardened materials, designed to withstand a constant bombardment that would instantly fry most consumer devices. This approach to engineering, prioritizing resilience over raw speed and redundancy over complexity, stands in stark contrast to our modern world of planned obsolescence. It is a powerful lesson in sustainability. What if we applied this deep time thinking to the challenges we face on Earth, building infrastructure, energy grids, and communication networks not for a few years but for centuries? The silent, ongoing success of these antique robots proves that creating for the long term is not just possible, it is one of the most profound legacies we can leave. That final whisper from the void will not be a dramatic event. It will be a slow, quiet fading, a gradual dimming of the signal until one day, the deep space network listens and hears only the background hiss of the universe. The steady heartbeat of data that has pulsed for over half a century will simply stop. The plutonium in their nuclear batteries will have decayed beyond the point of generating even a trickle of power, and the lights will go out on our most distant outposts. The conversation that began in an era of bell-bottoms and vinyl records will reach its inevitable end. For the scientists and engineers who have dedicated their lives to this mission, it will be a profoundly emotional moment, like saying a final, one-sided goodbye to an old friend who has traveled so far they can no longer call home. This silence, however, is not an ending, it is a transformation. These robotic craft will shed their roles as active explorers and begin their true, eternal voyage. Stripped of power and consciousness, they will become inert artifacts, the most durable relics our civilization will ever produce. For billions of years, they will drift through the calm, dark currents between the stars, untouched by solar winds and stellar storms. They will outlive our continents, our oceans, and even our sun. In their silent hulls, they carry the golden records, gold-plated copper discs containing the sounds and images of Earth. These are not meant for us. They are a message cast into the cosmic ocean with no expectation of a reply, addressed to any intelligence that might one day find this silent, frozen traveler. The probes themselves become the message, a permanent testament to a species that, for a brief and brilliant moment, looked up at the night sky, wondered about its place in the grand scheme, and chose to reach out. Their greatest legacy may not be the data they sent back, but the simple, profound act of their continued journey, a bottle in the galactic ocean carrying a story of a pale blue dot and the life that once flourished there. The quiet endurance of Voyager is about to be replaced by an audacious sprint. While our current probes drift slowly toward the stars, the next generation is being designed for speed, with a singular, breathtaking goal to reach another star within a human lifetime. The most ambitious of these concepts is Breakthrough Starshot, a project that sounds like it was pulled from the pages of science fiction. Its plan is to use a powerful, ground-based laser array to propel a fleet of tiny spacecraft, each no larger than a postage stamp and attached to a light sail, to velocities approaching 20% the speed of light. At that pace, such a probe could reach the Alpha Centauri system, our nearest stellar neighbor, in just about 20 years. This is not merely an upgrade to Voyager, it is a complete reimagining of what deep space travel can be. The primary target would be Proxima Centauri b, an Earth-sized exoplanet orbiting within its star's habitable zone. A flyby by one of these tiny craft would be fleeting, a blindingly fast passage lasting mere seconds. But in that instant, its miniature cameras and sensors could capture the first direct image of an alien world, resolving whether it possesses oceans, continents, or an atmosphere. It would also continuously sample the interstellar medium along its entire journey, analyzing the dust and gas between the stars with a precision far beyond what Voyager can achieve from the edge of our own system. These missions would do more than just explore a new star. They would begin to construct a genuine timeline for our entire local galactic neighborhood. By comparing the composition of the interstellar material around Proxima Centauri with our own, we could understand how the raw ingredients for planetary systems vary from one star to the next. We could learn if our solar system's particular mix of elements is common or a cosmic rarity, fundamentally rewriting the story of our own origins in a broader galactic context. The hurdles are staggering, requiring breakthroughs in laser technology, light sail materials, and miniature electronics. The financial cost is immense, and the risks of failure are high. Yet this visionary spirit is a direct inheritance from the engineers who first calculated the Grand Tour. It is the same human drive to push beyond the known, now focused on the ultimate challenge of freeing ourselves from the sun's gravitational and psychological hold, and finally stepping into the galactic ocean. These silent voyagers have done more than just visit planets. They have become time machines, sending back data that rewrites the history of our cosmic home. Every image of a volcanic plume on Io, every radar map of a hidden ocean on Europa, and every measurement of the solar system's frothy magnetic frontier has forced us to tear out a page from the old astronomy textbooks. Our solar system is not the quiet, orderly museum we once pictured. It is a vibrant and often violent neighborhood, filled with erupting ice, methane rivers, and worlds that defy every simple classification. The discoveries have been a continuous lesson in humility, proving that our assumptions about the cosmos are often just that, assumptions waiting to be shattered by a whisper of data from the void. This grand revision of our past is the ultimate gift from these robotic pioneers. They handed us a new, more accurate timeline, one where geological life thrives far from the sun's warmth and the building blocks of planets assembled in a gentle cosmic dance. Now, standing on the shoulders of these mechanical giants, we look toward the horizon. A new fleet of explorers is being prepared, equipped with sharper senses and more ambitious goals, ready to ask the profound questions these missions uncovered. They will not just map worlds, they will taste their oceans and sniff their atmospheres for the chemical signatures of life itself. The rewriting of our cosmic story is a tale with no final chapter, an endless pursuit of understanding driven by the simple, powerful human need to know what lies beyond the next frontier.